So the first part of this question wants us to state the defining equations for a Fourier series for a function f of x which has a period of 2 pi. So we need to look at the equations that were given at the start of the question. These are given for a general period L, and then we simply need to convert from a period L to a period of 2 pi. So wherever we see an L, we just replace it with 2 pi. So if we do this, we find that f of x is given by a naught over 2, and then it's the sum n equals 1 to infinity, and then it's an cos nx plus bn sine nx. So that's the definition of the Fourier series, and then we can write that a naught is given by 1 divided by pi. It's the integral between 0 and 2 pi f of x dx. An is given by 1 divided by pi, the integral between 0 and 2 pi f of x cos nx dx, and bn is given by a similar formula, 1 over pi, the integral between 0 and 2 pi f of x sine nx dx. So these are the formula that we need to use when our function has a periodicity of 2 pi, which is the case in this question. So the rest of the question requires us to find the value of a naught and then values of an and bn. So we'll start with a naught. A naught is given by 1 over pi, and then again it's the integral between 0 and 2 pi f of x dx. Now if we look at the function, we can see that the function is only non-zero between 0 and pi. If we take the period as being between 0 and 2 pi, between pi and 2 pi, it has a value equal to 0. So we can find a naught by taking 1 over pi, then integrating between 0 and pi. Over this range the function has a value equal to x, so we have to integrate x with respect to dx. So that gives me 1 over pi. If I integrate x, I get x squared over 2, 0 and pi. That gives me pi squared over 2 pi, which is equal to pi over 2. So that's the value of a naught. So we've now found the value of a naught. We now need to find the value of an. An will be given by 1 divided by pi. Again, we only need to integrate between 0 and pi, where the function is non-zero, and then we have x cos nx dx. This is a slightly more tricky integral than the integral we had for a naught. We're going to have to integrate this by parts. This is going to give me 1 divided by pi, and then I'll integrate by parts. I want to get rid of the x, so I'll call x the function u, and cos nx will be the function dv by dx. So the first thing is I need to integrate dv by dx. Cosine nx when integrated becomes sine nx, and we bring out a factor 1 over n, and then we have the limits are 0 and pi, and then we have minus the integral between 0 and pi. We now differentiate the x, that removes it, and so we're left with just the integral of sine nx over n dx, like that. Now we can look at the terms before we perform the final integral. We can hopefully see that the first term, the x sine nx over n, will give us 0, because sine is 0 at 0, and also integer multiples of pi. So we can ignore the first term, we just need to calculate the second integral. So continuing, we have a naught is equal to 1 over pi, and then it's equal to minus, and now we have to integrate sine nx. If we integrate sine nx, that becomes minus cos nx, so that takes out the minus, and there's an additional factor of n, so we get plus cos nx over n squared, and then the limits are 0 and pi, like that. So we now put in the limits, we get 1 over pi, brackets. In fact, we can bring the n squared outside the brackets there, and we're going to get cos n pi for the upper limit, and the lower limit is just -1 because cos of 0 is 1. We can look at this function now and see what values it has for various values of n. What we can hopefully see is that when n is even, an is equal to 0, because cos of n pi, where n is even, so cos of 2 pi, cos of 4 pi, etc. is 1, 1 minus 1 is equal to 0. When n is odd, however, cos n pi is -1. So an then is equal to -2 over n squared pi. So only the odd ans are non-zero, and these have a value equal to -2 over n squared pi. We now have to find the Bn coefficients using the expression that we wrote down previously. So Bn is given by 1 divided by pi, and it's the integration between 0 and pi of x sine nx dx. As was the case with the an coefficients, we have to integrate this by parts. We take the x as being the u function and the sine nx as being the dv by dx function. So this integrates up to 1 over pi, and then we integrate the sine nx, that goes to a cos nx, and as a factor of n comes out, so we've got in total minus x cos nx over n, evaluated at 0 and pi, and then plus the integral between 0 and pi of cos nx dx, and there's still the factor of n just there. Now if we look at the second term in the brackets, we can see that the cos nx will integrate up to a sine nx term. Because we're evaluating that at both 0 and pi, both those limits give us 0. So the remaining integral will give us no contribution to the overall value of Bn. So now we can find Bn by evaluating the first term in the above brackets at the two limits 0 and pi. So this gives me 1 divided by pi. The upper limit gives me minus pi cos nx over n, and the lower limit, because of the x factor there, gives me just 0. So we now have this expression for Bn. We can see there's a cancellation of the pi terms there, and so Bn is equal to 1 over n cos nx. Now we can simplify this slightly by remembering that cos nx is equal to -1 to the n. So because of the minus factor in the above equation, we can therefore write Bn in the following form. We can write it as 1 over n, and then -1 to the n plus 1. So we've now found the values of a0, an, and bn, so we can now write down the expression for the Fourier series. The Fourier series is going to be f of x is equal to pi over 4, that's a0 divided by 2, minus 2 divided by pi, and then it's the sum between n equals 1 and infinity, but only for odd n, and then there's a factor of n squared, and then we have cos nx, and then we have plus the integral n equals 1 to infinity. All the bn terms are non-zero, and so we write -1 to the n plus 1 over n. That's the expression for bn, and then we have our sine nx like that.